Welcome back to Edupedia world. In the recent classes, we have touched upon many things like the electrical energy, the electrical power, their units, what is the commercial unit of electrical energy. Then we saw Joules law of heating. So these formulas, in order to understand them better, we need to go into some numericals and apply them in order to understand those things. So this lecture is dedicated towards numericals, which will help you understand the whole concept holistically and help link between the different concepts. So let's start with the numericals. This is the first numerical that we are going to see. Here we have two coils which have resistance, one of 6 ohm and another coil of resistance 3 ohm. They are connected with a battery of 9 volt, and we are asked to find out what is the electrical power consumed by the system. So this part wants us to find the power consumed by the whole system, that is both the coils combined. Second part says what is the electrical energy consumed by each resistance. So we need to find out what is the electrical energy consumed by this and by this in 100 seconds. And finally we need to find the total energy consumed in 100 seconds. So basically the third part will be sum of the electrical energy consumed by 6 ohm and by 3 ohm. So let us start with the first part that asks us to find the electrical power consumed by the system. So to begin with, let us write what are the formulas we know about power. We know that power is VI, I square R, V square upon R. So these are the three relations we know about power. What do we have here? We have our voltage and we have the individual resistances. So if we find out the combined resistance of the system, then we can use the formula V square upon R to find the effective power consumed by the system, isn't it? So for the first part, let us find the R total, resistance total. Now the total resistance of the system is two resistance added in series. So for series we just need to algebraically add them, 6 ohm plus 3 ohm, that gives us 9 ohm. This is my total resistance. Now what do I have? The voltage is 9 volt. So what this means is we can replace the 6 ohm and the 3 ohm resistances by a single resistance of 9 ohm, which is connected by a 9 volt battery, connected across by a 9 volt battery. Therefore the power can be found out to be V square upon R. V square is 9 square upon resistance is 9. That gives me a power of 9 watt. So for this combination the power rating is 9 watt. Now what if the question asked us to find the power rating for the individual resistances? Say we had to find what is the power consumed by the first resistance and what is the power consumed by the second resistance. Let's assume that the question had that part. Then how to approach the question? In order to do that, we cannot use the formula V square by R, since the V square for the individual resistances we do not know. We do not know what is the potential drop across this resistance and what is the potential drop across this resistance. Rather we know the total potential drop. So we cannot use this directly. Alternatively what we can do? We know the resistance, individual resistance. If somehow we found out what is the current flowing through each of them, then we can use the second formula to find the power rating for each resistance. Fine. So let us use this formula. To do that, we need to find out the current flowing. A point to note, since the circuit is in series, the current flowing through the first resistor will be equal to the current flowing through the second resistor. Therefore, we can use Ohm's law of I is equal to V by R. My V is 9 volt and total R is 9 ohm. That gives me a current of 1 ampere flowing through the first resistor and the second resistor. Using that knowledge and using the formula for power as I square R, let me find out the power through the 6 ohm resistor. That will be I square R, where I square is 1 square and R is 6. That gives me 6 watt. So the first resistor is consuming 6 watt of power. The second resistor, we will use R is equal to 3 ohms. That will give me 1 square times 3. Again, the current is the same for both because they are in series, and this gives me 3 watt. Ultimately, we see that the power consumed by both of them combined is 9 watt as we have initially calculated. So that verifies our calculation. Now let us jump into the second part of the question. The second part says that we need to find out the electrical energy consumed by each resistance in 100 seconds. Okay, so electrical energy is basically power multiplied by time. Now if we find out the power consumed by each element, we can just multiply it by time and find out what is the electrical energy consumed by each element. That is exactly what we have just done. We had found out the power of the 6 ohm and of the 9 ohm, rather the 3 ohm resistance. Therefore, we are going to use these values of power and plug it into the formula and find out what is the electrical energy consumed by both the elements individually. So electrical, let me write EE, electrical energy consumed by 6 ohm. That will be power times the time. Power for the 6 ohm is 6 watt and my time of running of the elements is 100 seconds. So that gives me a 600 joule energy consumed by the first element, that is the 6 ohm. Similarly, the electrical energy consumed by 3 ohm will be power consumed by this 3 ohm times the time for which it is running. That gives me 300, that is 300 joule of electrical energy is consumed by the 3 ohm resistor. Now the final part, using this two information, we can find the total energy consumed in 100 seconds. That is basically energy consumed by 6 ohm resistor and the energy consumed by 3 ohm resistor, which adds up to 600 plus 300, and that gives me 900 joule of energy consumed by both the resistors combined. This total energy consumed can alternatively found out by using a different relation. What relation can be used? Let us write down the relations which we have for the energy. Energy can be written as I square RT VIT V square divided by R times T. Now what we know is the current flowing through the system. That is the same current flowing through both the system. We know the potential difference applied and we know the time. So we can use this relation to find the total energy consumed. Let us calculate using this relation. Or E total is VIT, where I is the total current and V is the total potential difference across them. V is 9 volt. Current is, as we calculated here, 1 ampere, and my time is 100 seconds. That gives me a 900 joule of total energy consumed, which is exactly equal to the value which we calculated using the individual components of energy consumed. So what we see here is then that we can use multiple approaches to solve the same question. You just need to see what is the values available and how you can manipulate them to give the required information. Okay, now let us jump into a different question and try to solve that. Okay, so the second question that we have is quite similar to the first question, as in we need to find out the same things. The only difference, even the values are same, the only difference is the resistors are now in parallel rather than in series. So let us see how that will affect our calculations, and this will also give you insight into parallel circuits and series circuit. So that is the idea of keeping everything constant. To begin with, we need to find out what is the total power consumed by the system. So in order to do that, again let us write out what are the possible formulas. Power is VI, I square R, V square upon R. So if I use the first thing, VI, then I need to find out the current flowing through each resistor. Because here we have resistors in parallel, therefore current will break and the resistors will have different current passing through them, right? If we use the second formula, then we can use I square R. Again we need to find out the current through each resistor in order to find out the power. But if we use the third formula, V square by R, we have the voltage, total voltage across them, and it is the same for both of them. And if we apply to each of them, then we can find the power through each of them and add them to find the total power. Okay, so let us do it the other way. Let us find the individual powers and then add them up to see the total power. After that, we'll see an alternative way to do it. So power through the 6 ohm resistor will be V square upon R, V square upon R. V is the potential difference across that resistor, which is the same as the battery potential difference, that is the terminal voltage, because they are in parallel. That turns out to be 9 times 9 upon the resistance is 6. 2, 3, 27 by 2, that is 13.5 watt. This is my power through the first resistor. Power through the second resistor, that is 3 ohm, will be similarly V square by R. Here the R will be 3 instead of 6, but the voltage drop will be same, since the voltage drop here is also 9 volt. 9 square upon 3, that gives me 3, and that is 27 watt. Fine, that was quite easy. The power through each resistance. Power total will be power through 6 ohm plus power through 3 ohm, which will be 40.5 watt, isn't it? 27 plus 13.5, that is 40.5 watt. So we have found out the total power and power through each resistor. If you remember correctly, then the total power in our last case, in the case of series circuit, was 9 watt. Here it is 40.5 watt. That is quite a hike. So just by changing the configuration of the resistors, we have increased the amount of power we are extracting out of the system. Fine. Now let us see an alternative way to do the same thing. What is the alternative way? The alternative way, what we can do is we can simplify this circuit by finding the total resistance here. The total resistance R total will be 1 upon 3 plus 1 upon 6. Since they are in parallel, the reciprocals will be equal to the sum of the reciprocal. That gives me 2 plus 1, and that is 1 upon 2. So my R equivalent is 2 ohm. Now if I use this information, this resistance, equivalent resistance, and if I use this wattage 9 volt voltage, then what is the power total? Power total will again use the same relation V square upon R, but now the R will be the total R of the circuit, and voltage will be same, 9 volts. So 9 times 9 upon 2, this is 81 upon 2, that is 40.5 watt. So by this alternative method also we got the same power output. That verifies that our calculations are right. Fine. Now let us see what is the energy consumed by each resistor. This should be pretty straightforward now, because we have found out the power by each individual resistor and also the power consumed total by the total circuit. So the part 3 and part 4 should be pretty straightforward. Even then, let's calculate. Energy by 6 ohm is power for the 6 ohm multiplied by time. That gives me 13.5 times 100, which is 1350 joule. Energy by 3 ohm, power 3 ohm times time, that is 2700 joule. An interesting thing, if you have noted, is that the higher resistance is actually using less power, and as a result less energy. The lower resistance is using more power, and as a result more energy. Why is it so? Think about it. And finally, the total energy is, we can either just add them up, or we can use the total power and multiply them by 100. Either way you will get 4050 joule. Okay, so we see that this question, the total energy consumed, has also turned out to be larger than the previous in series question. The power consumed has turned out to be larger than the in series question, and the interesting point to ponder is the higher resistance is using less power and less energy, which was not the case in the first scenario, that is in series. In series, if you go back and see, the higher resistance was using more energy compared to the lower resistance. So I will leave it upon you to think through why exactly that is happening. Let's see one more question. This question says that we have an electrical appliance which has a rating of 1 kilovolt ampere and 220 volt. We need to find out what is the energy consumed by this appliance in 2 hours of usage in 2 units. One is kilowatt hour, second is in joules. Finally, the question says if that the commercial unit is 4 rupees per unit, what is the cost for 2 hours of operation? Okay, so what are the given information? This is a unit of power. How do we know that? I will elaborate. Power is 1 kilovolt ampere. We know that power is V times I. Voltage is V, amperes, current is expressed in amperes. So basically this is voltage times current, therefore this is a unit of power, and this alternatively can be written as watt, and there is a kilo. So basically the power rating is 1 kilowatt, right? Next we have the voltage rating as 220 volt. we have said that the appliance runs for 2 hours. Time is equal to 2 hours. And we are asked to find out the energy consumed in kilowatt hour and in joules. So energy in kilowatt hour. Let us find out. Energy in kilowatt hour will be power multiplied by the time of operation. Now the power we have converted to kilowatts. Let us use that. How much is the power? 1 kilowatt. What is the time of operation? 2 hours. Combining these two, we can get the energy in kilowatt hour as 2 kilowatt hour. So we have found out that the appliance, if runs for 2 hours, will use an energy of 2 kilowatt hour. Now let us calculate the energy in joules. Energy in joule. Either we can use directly the transformation value that we saw in the lecture, or we can calculate it for our own self. Let us calculate. 2 kilowatt hour can be written as 2 into 10 power 3 watt hour. Joule is watt second, power times second. So we need to convert the hour to second. Let us do that. 2 into 10 to power 3, 1 hour is 60 minute times 60 second, and that gives me this many watt second, and watt second is joule. Therefore combining these things, 60 times 60 is 3600 times 2 is 7200, that is 7200 10 to the power 3 joule. We can simplify this at 7.2123. So 3 multiply with this and we get 10 power 6 joule. Therefore the energy consumed by the device in 2 hours is either 2 kilowatt hour or 7.2 into 10 power 6 joule. Now the third part of the question says that if the commercial unit is rupees 4 per unit. What is the commercial unit? As we have discussed, one commercial unit is equal to 1 kilowatt hour. Therefore 1 kilowatt hour corresponds to rupees 4. But how much kilowatt hour is being used in 2 hours? 2 kilowatt hour is being used. Therefore the cost will be equal to energy in commercial unit or in kilowatt hour multiplied by cost per unit. This gives me simply 2 kilowatt hour into rupees 4 per kilowatt hour, and that means we need rupees 8. Let me rectify it. Rupees 8 in order to operate this device for 2 hours. So we have seen how we can easily calculate the different requirements of the question by using the appropriate formula to arrive at it. And sometimes we need to intelligently tailor the formula as per the requirement of the question. Fine. So these 3 questions that we have discussed today should have given you a lot of insight into how to go about solving numericals concerning the electrical power, electrical energy. And one thing that I did not cover in this exercise section was Joules heating effect, but we can use that concept and combine it with the idea of calorimetry. In calorimetry, what we had was basically there was either loss of energy or gain of energy. So basically there we can, for the supply of energy, we can use a filament coin which heats by the Joule heating effect, and we can use I square RT to calculate the amount of heat generated, and that can basically be used for calorimetric calculations. But I'm not going to go into details about that application. You know the formula, you have already seen about calorimetry, and you can combine the two concepts and practice numericals on your own. Okay, so with this particular question I will close today's lecture. Till the next lecture, have a great day. Goodbye.